All right, chemists, we'll get started. Good morning, everybody. So some announcements before we get started with where we left off on Monday. There's no lecture on Friday, so this will be our last lecture of the week. So go off and enjoy our long Memorial Day weekend. I'm going camping, and I will have no electricity and no internet. So if you email me, I will not get back to you until Tuesday. Unless I go into town, and then I will have internet. But anyway, enjoy that weekend and our break. But we're going to pay the price for that because we won't finish midterm 2 material until Wednesday next week. But I do anticipate we'll get through like 95% of it today. Midterm 2 includes the first about 20 slides of chapter 16. Those slides are already posted. We will get to that today. With that said, midterm 2 practice exams are already posted, so you can use this weekend to get ahead on your midterm 2 preparations. And then we will do a midterm 2 review on Wednesday next week, since that's the day before the midterm, the same way we did Monday's review. I'll post more information about that in my weekly recap announcement at the end of the week. So anticipate the same deal for midterm 2, which is in recitation in a week. So you have 2 graded activities, then you'll have midterm 2. With that being said, I looked at our midterm 1 results, and I'm quite happy. So our midterm 1 average was about a 66%, which is actually really great. That's really good. If you weren't aware, so just to put it into comparison, last year when I taught over the summer, the average was a 55%. Yes, and so, but I made changes. So this term over the summer, we're doing in recitation exams, which we've collected a lot of data, and it's had a lot of positive impact on student performance. When I teach in previous years, when I taught over the summer, they were during lecture, and they were longer. They were a lot longer, so it was about twice as much material on those in-class exams. So recitation exams seems to have a very positive influence on student performance. 66%, I'm really happy with that. So keep up the good work for midterm 2 coming up. All your resources are available to you, and then we'll do some review on Wednesday. I'll post a new packet or whatever, but keep up that great work. Okay, so those are the announcements. Okay, so we'll continue on with chapter 15, chemical equilibrium. This is where we're talking about big K. A big portion of this chapter, chemical equilibrium, is the introduction of ice tables. So we looked at a couple ice table examples earlier where I gave you information about a chemical equilibrium, and through that information, the initial and equilibrium concentrations, you were able to fill in the entire ice table, including the change line, to figure out your equilibrium concentrations and calculate K. In this example, this is what I call a type 1 ice table, where you just kind of like Sudoku it. You like fill in the missing pieces based upon your change line, and you calculate K. You don't have to use the quadratic formula ever for questions like this. But on Monday, we left off on a question where we did have to use the quadratic formula. How this question is phrased is a little bit different. I give you initial concentrations, and I give you K. You have to calculate the equilibrium line. You have to calculate X. So when you calculate X, what we saw when we threw that equilibrium line into our Kc expression, we got something that looked like x squared. All right, let's rewrite this. X squared over 0.1 minus x equals K, which was given. This requires the quadratic formula. We in the chemistry department are not assessing you on can you use the quadratic formula to get an answer. We want to use chemical intuition and kind of some tricks to kind of speed up the calculation. And so the approximation that we make here is we say, oh, this X is going to be really, really small. And so if X is really small, we can ignore it in the calculation, and it becomes a much more straightforward expression. I know X is going to be small because K is is small, that at equilibrium, you're not actually going to make a lot of products. So you're actually not going to lose that much reactant. And so when you make the approximation, you get X is equal to, times 10 to the negative 6. That is a tiny number. Do 0.1 minus 5.6 times 10 to the negative 6, it is basically still 0.1 in terms of sig fig. So that's why we can make the approximation. And so on this slide, I talk about the approximation that we make. Again, the approximation you'll usually make with these, I give you initial concentrations, I give you K, you solve for X, is you make the approximation that this X minus X is very, very small. So we can just ignore it. And the calculation becomes a lot simpler. We usually do this when K is really, really small, and we'll do this a lot in chapter 16 and 17. And just to kind of prove it to you that the answers are exactly the same, I put the full quadratic form into Wolfram Alpha. I used the quadratic formula to calculate X. Note that with all quadratics, there's always two answers, but we want to choose the answer that makes sense here. X needs to be a positive concentration, and so we see the answer is 5.47 times 10 to the negative 6. When we make the approximation, you can just do this one on your calculator. It's K times the denominator, take the square root. You get that the answer is 5.747 times 10 to the negative 6. It's literally the same answer, and that's why the approximation works. All right, so let's do another example from the beginning. So this is another type 2 where we may or may not have to use the approximation or the quadratic formula. So here are our initial conditions. So since this is chemical equilibria, we want to write out that ice table. So go ahead and put in our knowns. I tell you the initial concentration of AB is 0.5. All of this is in molarity. For ice tables, they should all be in molarity if it's Kc. If it's pressures, then Kp. So that's 0.5 molarity, A is 0.1, and then B is 0.1. All right, great. So in all of the other examples, it was usually obvious which way the reaction needed to go. Like in the previous example, all right? We started with only reactant. The reaction has to go forward. In another example, if there was only product, the reaction has to go backwards. But in this one, there's reactant and product present on both sides, so it's a little bit trickier to figure out which way does the reaction go, forward or backwards. So to predict which way the reaction goes, what we want to do is actually calculate Q, given these initial conditions. And so we talked about this earlier, where Q is the same expression as K, it's just you put in non-equilibrium condition concentrations. When you compare the values, magnitudes of Q and K, you can predict which way the reaction shifts. I like to think, oh, I have too much reactant or product, then I have to shift this way to achieve equilibrium. So let's go ahead and calculate Q using that K expression. The K expression for this reaction is simply going to be reactants over products, or sorry, products over reactants like always. So Kc is A concentration times B concentration over AB concentration. But we want to calculate Q. So we're going to plug in those values that they just gave us. All right. Q is going to be 0.1 squared over 0.5. And so if you calculate that, I think Q is equal to 0.02. So let's compare this number, Q, 0.02, to K, which is 0.001. So when we compare Q to K, 0.001, Q is obviously bigger than K. So think about what that means. You don't have to memorize, the different trends or anything. If you just remember Q and K is products over reactants, and Q is a bigger number than K, you have too much what right now? Reactants or products? You have too much products, yeah, because remember, it's products over reactants. And so if Q is a bigger number, there's a bigger number in the numerator, right? And so you have too much products right now. So which way does the reaction shift, forward or backwards? Backwards. And so this one's a little bit trickier because of that fact that it's not quite obvious which way the reaction shifts, what the signs are in your change line, but we can figure it out via Q. All right, yeah, so I like to think too much product right now. And so this reaction is going to shift backwards. So let's go back to the ice table. So that means the reaction is going to shift backwards. So the reactants are now the products, and the products are now the reactants. We don't have to flip the reaction. All we're going to do is just change the signs in the change line. We're going to consume products now. So we are going to lose a little bit of A. How much B will we also lose if this reaction moves backwards? Minus X. But then how much AB reactant, how does that change? It's going to be an X amount, but what's the sign there? Plus X. Yes, it's plus X. So here I'm showing you the reaction moved backwards, where the reactants, you're gaining that, so it's plus X. The products are minus X. Those are being consumed. I'll compare this to another one where the reaction moved forward. In this one, this reaction moved forward. It's minus X on the reactants, plus X on the top. We're still going to do this the exact same. We're not flipping the reaction at all. We're just doing it backwards. And so we'll just go ahead and add up those columns. So at equilibrium, you should have a 0.5 plus X amount of your reactant and a 0.1 minus X of both of your reactants. All right. And so the trick with ice tables, remember, is that your equilibrium line always goes into the K expression. So I'm going to rewrite that K expression. Those are our equilibrium concentrations. We know the K expression is A times B concentration over AB concentration. So I will stick all of those things, the equilibrium line concentrations, into this. So 0.1 minus X times another 0.1 minus X. So this is 0.1 minus X squared, simply. And then we will divide by the AB concentration, which is 0.5 plus X. Equals, we are given K, it's 0.001. All right. So that is an expression that we can solve. There's an X on the top and the bottom, and that's a problem because right now this requires the quadratic formula. Something I could do is, distribute that square, put it into the, the quadratic formula form, but I don't want to do that. Okay, I don't want to do the quadratic formula because I'm lazy and I don't want to spend precious exam time doing the quadratic formula. So what I'm going to do instead is use another approximation. Again, we will think, because K is very small in this case, or you can think the concentration of AB is very large, 0.5, I'm going to make an approximation and say that this plus X is going to be a very, very small number. It's usually when there's an X in the denominator, it screws us up and it requires the quadratic formula. So the approximation I'm going to make is I'm going to say that plus X is very, very small. It's small compared to the number that I'm adding to it. So if I add a very, very small number to 0.5, that 0.5 is barely going to change. So the approximation I'm going to make here is say that this plus X is very, very, very small, and so I can just ignore it. All right, this is the approximation. And so now if the expression is 0.1 minus X squared over 0.5, this does not require the quadratic at all. To calculate this, you would just multiply these two, the denominator and K together. You take the square root and you just solve for X. There's no quadratic necessary here. And so what you get here when you solve for X is, with the approximation, the answer is 0.078. That's with the approximation. If you were to go on and do the full quadratic formula and not approximate, that answer is actually 0.076. So do these answers differ that much? They don't differ that much, and on an exam, the tolerance will be large enough that as long as you're close enough, like 0.07 something, then it'll still be marked correct. And same goes for online homework as well, when an approximation is necessary. So I'll prove to you that you can use tools online, especially for online homework, to help you with these. Whether an approximation is appropriate or not. Usually it's when K is a large number. So here is my favorite app is website is Wolfram Alpha. It calculates things for you, so you don't even have to put it into quadratic formula form. You are free to use this website on online homework. Because our exams, there's always an approximation that can be used. But I'll prove it to you that the approximation works. So here is the exact expression we got when we finished up that ice table. 0.1 minus x, that whole thing squared, over 0.5 plus x equals that k value. So this is without the approximation. I'll show you the answer. All right, there's the answer. The solution is 0.076. All right, so remember that in your brain. So now let's do the approximation and see if the answers match. So if I do it like this, without the plus x on the denominator, you can very straightforward put this into your calculator and solve for it. Solve for x pretty straightforward without needing to expand that numerator. So the solution that Wolfram alpha gives us here with the approximation where we get rid of that plus x on the denominator is 0.78. So very, very close enough that on online homework or exams, the tolerance is always large enough where it will accept that answer as long as x is small enough. And so in this case, because x is being attached, it's being added to this 0.5 number, which is pretty big, that's why this approximation works. All right, so we got the value of x. X equals let's just say it's 0.076 or 78. All right. I solved for x. Is that my answer? No, it's not, because you got to look back at what the question wants. Just because we solve x, this isn't math, all right, where it's like you solve for x and you're done. You need to see what does x represent and how does that relate to what's actually happening in this reaction. I'm asking you calculate the equilibrium concentrations of everything, all the species at equilibrium. So I want you to tell me what is the actual numerical value of all of those equilibrium concentrations. So in this case, x is not our answer. I actually have to shove x back into that equilibrium line, and then those will be my answers. So x is not my answer. Gotta put those back in to the equilibrium line. So that means my equilibrium concentrations are 0.578 molarity for AB. And then what is this? Oh yeah, these ones are wrong. I think this one's wrong. This should be, these answers are wrong. I did the plus x minus x incorrectly. So I'll just write the answers right here. What is this? 0. What? 0, 0, 1, 2, 2, 2, 2, 2. Okay, perfect. All right, molarity and A, B are the same, so 0.022 molarity. There we go. All right, and let's see. Let me 0.022 squared divided by 0.578. Yes, all right, so there are answers. That's what you would actually report on an exam or on online homework, not necessarily X, given this question. All right, so there is another ICE table approximation question, so let's do one more. And then we're done with these tougher calculations. Let's look at this one. Okay, it's another ICE table, so I'm giving you initial concentrations and K. Calculate equilibrium constants, or equilibrium concentrations. So just like before, we want to plug in these initial concentrations that are given into our ICE table. Here we're working with pressures, but I give you Kp, so that's fine. We just work it the exact same way. We don't have to convert any of these things into molarity since we're using Kp, and P stands for pressures for gases. So here I tell you that the initial concentration of A is 0.5 atmospheres and B is also 0.5. So that means I start with no reactant. All right. Which way does this reaction have to go? Backwards, yeah, since I have no reactant. So it's negative x on my, or minus x on my product side, and then what's on my reactant side in the change line? Plus 2x, very good. Yes, that's tricky because of the 2 stoichiometry. Yep, okay. Then we add up those columns like always. So at equilibrium, you will have a 2x amount of that reactant, and you will have a 0.5 minus x of both the A and B products. So this is no different like we've done previously. Okay, so once we have our ICE tables, the E line always goes into the K expression. So our K expression, in this case it's Kp, is equal to products over reactants. So pressure of A compound, pressure of the B compound over the pressure of the AB compound, but it is squared. So no different as before. So I'm going to stick those equilibrium concentrations in here. So 0.5 minus x twice, so it's going to be squared over 2x. But that whole thing is squared because it's 2ab. So note the square there, all right, very important that stoichiometry follows through into the K expression. All right, and so just like before, we have our K expression, and in this question, I give you what K is. It is 100, all right? So at this point, a lot of students will be like, oh, I can make an approximation, right? But actually, I don't want to here. This is a very special kind of question where you actually don't need to use an approximation. You can solve it just using math, algebra. The quadratic formula isn't necessary. Also, K is a really big number, so we can't really make that approximation, oh, we say X is small, get rid of it. We can't say that because K is a big number here. So this is the trick for this particular type of question. It's actually a perfect square. This ice table is a perfect square because there's a square on both the top and the bottom. And so I'm not very good at teaching math, but if there's a square on the top and the bottom, you can take the whole square root of the that side of the equation, but you also have to take the square root of the other side. And so what that does is get rid of the square. So 0.5 minus 2 over 2x. So now the square went away on that side, but now it is equal to 100. It's equal to 100. Does this require the quadratic? It does not. You just have to move the variables around and isolate x to solve for it. I will do that work, for you to prove to you I know how to do math. All right, so what I'm going to do here is multiply both sides by 2x. So that isolates 0.5 minus x on the left side is 200x. Oh no, well, it's not equal to 100, it's equal to 10. Sorry about that. Forgot to take the square root of 100. It's not 200x, it's 20x. There we go. All right, so I just moved that 2x to the right side, and so add both sides by plus x. So then you get 0.5 equals 21x, right? No quadratic needed. This is just straight algebra. And so you can see it's quite straightforward after you take the square root of both sides because this example is a perfect square. So I think I get that x is equal to 0.0238. And this would be atmospheres because this is Kp. All right, is this my answer? No, look at what the question wants. I want you to calculate all of the equilibrium concentrations. So that means we have to take that x and shove it back into the equilibrium line to actually get those concentrations. So that means at equilibrium, you're going to have, 0.042 atmospheres of your reactant. And you will have, both of these will be 0.476 atmospheres, all right? And so to check your work, you can plug those concentrations back into the K expression to see if you get the same value of Kp out. If you do 0.476 atmospheres squared over 0.07 or 0.047 ATM squared, you should get 100 back out. And that's the beauty of those equilibrium concentrations, always relate to your K value. In this case, it's given, it is 100. So in this example, no quadratic formula is needed, all right? If you are to make an approximation when you shouldn't make an approximation, you will get the wrong answer because in this case, X is it's a large enough number that it's going to make significant difference if you get rid of that minus x, let's say, in the numerator. If you solve this getting rid of that minus x when you didn't need to, your answer will be off enough that it might not count correctly. So note here that this is a perfect square. You can solve it just using algebra. No quadratic is needed, all right? So that's the last type of ice table. Sometimes with these types where you're calculating equilibrium concentrations, you might have to use an approximation. But here's the thing, if you do the quadratic formula, if you put in the K expression into Wolfram alpha, you will always get the right number. There's only certain instances where using an approximation will speed up time, and that's usually when X is a very, very small number compared to concentrations that you start with. All right, so those are ice tables. The numerical kind, we can put our calculators away for a little bit because we're going to move on to the last portion of this chapter, and this is actually a concept that you will do in lab. This is the LCP lab, where we will look at just kind of conceptually how can we disrupt these chemical equilibria. Equilibria are reversible reactions. So you can make them go forward, you can push them backwards an infinite number of times. So Le Chatelier's principle helps us predict how those disruptions affect chemical equilibria and help us predict which way a reaction has to go. So things to recall here, when a reaction is at equilibrium, the overall forward rate is equal to the overall reverse rate. But if we disrupt an equilibrium, let's say by like adding more reactant or adding more product, at that moment when we disrupt it, we're actually not at equilibrium anymore. And so the reaction is going to shift itself so it achieves equilibrium again. So what Le Chatelier's principle does is help us predict how does that reaction achieve equilibrium again. And so when we're at equilibrium, and we do products over reactants, we are looking at the value of K. But when we're not at equilibrium, say we make a disruption, at that moment we make a Q condition because we're not at equilibrium. But comparing the values of K and Q help us predict which way they have to go. All right, so just to kind of recap, we already talked about this comparing Q and K. Reaction quotient Q is just the expression of K, but those concentrations are not at equilibrium. So important when we make those disruptions. And so to predict whether a reaction has to move backwards or forwards, it's just like when we did ice tables. You think to yourself, okay, if Q is bigger than K, you have too much products. The reaction moves backwards. But if Q is smaller than K, you have too much reactants. The reaction has to move forward. If Q is equal to K, then that means you're already at equilibrium. All right? So yeah, Q tells us many things. It tells us how does the reaction shift itself to establish equilibrium again. And what we'll look at a little bit closer here is it also tells us a little bit about the rates of the forward and reverse reaction the moment you make that disruption. So we're going to study 3 different types of disruptions to reactions. The first one is adding or removing products or reactants, so changing concentrations, right? Changing concentrations, like at a certain moment, will disrupt your chemical equilibrium. The reaction has to adjust itself to get back to equilibrium. We'll also change the pressure. This is important for gases, and so we'll look at that. And then finally, the last one we'll look at is changing temperature, right? So we will learn Le Chatelier's principle 2 different ways, the quick and dirty way and then the real way, right? So I think we'll start with the quick and dirty way, okay? Because the quick and dirty way helps us just predict which way the reaction shifts. It's like, okay, you add reactant, the reaction shifts forward. You add product, the reaction shifts backwards. That's the quick and dirty way. But what we'll look into deeper is why does the reaction shift left or right when we make these disruptions? It actually has to do with rate laws. So here's the quick and dirty way. When you make a disruption to a reaction at equilibrium already, the reaction shifts to undo what you just did. Okay? So if you add reactant, the reaction's going to shift towards products, because when you shift towards products, you consume reactant and you make more products. And that's how Q gets back to K. Let's say you have a reaction at equilibrium and you add products. Now you have too much products. The reaction's going to shift backwards to consume that product to get rid of what you just added and make more reactants at the same time. So the equilibrium will do the opposite of what you just did to undo that disruption. So an analogy would be like a seesaw, where at equilibrium your seesaw is like this. Let's say you add you add reactant, so it lowers this side. The reaction is going to shift itself by moving towards this direction, the opposite direction, to get back to equilibrium. Or if it shifts this way, the equilibrium will go back like that. So this is just again, the quick and dirty way. If you add nitrogen to this reaction, so we're adding stuff to the reactant side, which way does this reaction shift, forward or reverse? Forward. Yes, it goes forward. You add this, it pushes it this way. So this reaction goes forward if you add nitrogen gas. Let's think about it a little bit differently, because we can add reactant, add product, but we can also remove stuff. So let's say we remove ammonia. Okay, so I like to think, okay, if you remove ammonia, you've created this void on the product side. So which way is the reaction going to shift? Forward or reverse? It's going to go forward again because you just removed ammonia. The reaction is going to shift to replace that ammonia that you just took away. So in both of these examples, the reaction shifts forward. But the difference here is in one you added and the other you removed. Here, this is just the quick and dirty way to predict which way the reaction goes. That the reaction just moves in the direction to undo what you just did, all right? But why? Right, why? Okay, that's the quick and dirty way. What's actually happening is when we disrupt an equilibrium, what we're actually doing is disrupting the rate law at that moment, all right? So the question is, why does the reaction move forward? Look, in this example, all right, in these two examples, both of these actions pushed the reaction forward. So your inclination or your kind of first instinct might be, oh, the forward direction increased its rate or something, because doesn't that push something forward if you speed it up in the forward direction? Yeah. But it's actually a little bit more complex than that. And it's the idea of chemical equilibrium. Both the forward and reverse reactions are happening at the same time. All right, so this is what's actually happening when we disrupt an equilibrium. We disrupt those rate laws. So let's go back to the example. Let's add a reactant. So in this case, let's add hydrogen gas to this reaction. What does Le Chatelier's principle predict? When we add hydrogen, which way does the reaction go? Forward or backwards? It goes forward. So that's in to the right. Yeah, so forward. When we add hydrogen, because we're adding a reactant, okay? But let's think about what's actually happening. Remember, chemical equilibrium is the forward rate equals the reverse rate. This is a elementary reaction, meaning that the forward rate has a rate law based upon the reactants and its stoichiometry, is equal to the reverse rate constant, which is equal to the reverse rate, which is equal to the reverse rate constant times the concentrations of the products. So let's remind ourselves how we get our big K. It actually comes from our rate laws. Forward rate equals reverse rate. So here I've just written the rate law for the forward reaction and the reverse reaction. Okay, so how are we disrupting this? We are adding hydrogen. So that means, how is the concentration of hydrogen changing at that moment? If we're adding hydrogen, that concentration's going up. Yeah. So let's go think back to kinetics. What happens to the forward rate when we increase the concentration of hydrogen? That forward rate is going to increase. Yeah, because this number increases. So the forward rate increases. What happens to the reverse rate law? Does anything change about the reverse rate law? No. Yeah, it actually stays the same. It stays the exact same. But why does it stay the exact same? This is the reverse rate law. Did anything about this change? No, nothing about that changed. I didn't change the concentration of ammonia at all, so there's no change here. So when we think about this, the forward rate speeded up the moment you added hydrogen, but the reverse stayed constant. So when those two opposing forces happen at the same time, we will see an overall shift in the forward direction, right? So that's what's happening here. Okay. All right, let's do another one. So what we see here, the moment that we add hydrogen, the reaction is going to shift forward. So what's going to happen is the concentration of hydrogen is going to go down. Nitrogen concentration is also going to go down because that's also being consumed when we move forward. And then over time, ammonia concentration increases because we increased the forward reaction rate momentarily until they're both equal again. Okay, so let's do another one. Suppose we add ammonia this time. So which way does the reaction shift when we add ammonia? It goes backwards, yes. Okay, so let's draw what this will look like if we add ammonia. So I started with the disruption. So here the reaction is initially at equilibrium, but then we disrupt the equilibrium by spiking it with a ton of product. So let's draw the graph of what it'll look like once it achieves equilibrium again. So if the reaction moves backwards, how will the concentration of this red line of ammonia change? It's going to go down. Yes, because it's moving backwards. But how down does it go? Does it go like this? Does it go back to where it was? What's actually going to happen is it's going to go down, but it's going to actually be a little bit higher than what it started with. And the reason is because we added ammonia, we added more material to this entire equilibrium. So it's going to go back down, but it's not going to go back down to where it was originally. All right? So note here that it's a little bit higher than where it started. Okay? So, and that's a little tricky. So ammonia goes down because we're consuming it. So then how does hydrogen concentration change? It goes up. Yep, it goes up. So it's going to also be higher than what it started with. And here, you know, once it starts leveling out, that's when we're at equilibrium again. And then also with nitrogen also is going to go up. But I should be a little bit more careful here. Do both of these lines for hydrogen and nitrogen go up the same amount? They don't. How are they going to differ? Hydrogen, its line's going to be higher, yeah, because you make actually 3 hydrogens for every 1 nitrogen. So very good. So the nitrogen's just going to go up like a little bit, and I'm going to really exaggerate hydrogen. It's going to look like that, all right? Okay, so there are all the lines. Everything we see is higher than where it started. Everything's higher than where it started. So once equilibrium is established, hydrogen and nitrogen are higher than what they were initially because this reaction's moving backwards, but a very important and overlooked detail is ammonia is also higher than it was originally because we added NH3 to the system. We added more material. So it's not going to go back down to where it was originally. Okay, so there we go. All right, so let's look at this, another example. All right, suppose we remove ammonia from this system. So we remove ammonia. So which way does the reaction shift? So just do the quick and dirty way first. It goes forward, yes. Okay, you remove ammonia, it has to shift forward. So that means if it shifts forward, I have to consume hydrogen. I have to consume hydrogen and nitrogen, so nitrogen concentration is going to go down. Hydrogen concentration is going to go down and more steeply because of that 3 coefficient. And then the ammonia concentration is going to go up. But is it going to go back up to where it was originally? It is not. It's actually going to go up and be slightly lower than where it was originally for the same reason as the previous example. In the previous example, we added more matter to the system, so everything increased concentration. But in this example, we're removing matter from the system, so everything's going to be lower than what it was originally. So here, note that ammonia concentration goes up, but not to where it was originally. So here, everything is lower than what it was initially because we're moving in the forward direction, all right? Forward direction, we still gain ammonia, but it just doesn't get quite back up to where it was. All right, so let's think about this example a little bit deeper, all right? Because I mentioned before, if I remove a product, the reaction moves forward. If I add a reactant, which way does the reaction shift? Also forward, right? So when we did the hydrogen example, we said add hydrogen, the forward rate law speeds up at that moment. That's why it shifts forward. So you might think, oh, in this example, we remove ammonia and the reaction shifts forward. So does that mean the forward direction speeded up? You might think that at first, but the reason the reaction shifts forward is actually for a different way. Let me give you an analogy, all right? Okay, pretend I'm walking on a treadmill. I'm walking on a treadmill, and you're watching me, and I'm making no net movements, right? Like that my forward walking pace is the same as the treadmill's like belt, all right? So I'm like using the treadmill normally. There are two ways I can go flying off the end of the treadmill. There's two ways. What happens if I just stop moving or if I slow down? I fly off, right? If I slow down. What's another way I can go flying off? If the what? If the treadmill speeds up, yep. So same idea here. There is actually two ways the reaction can shift in the forward direction, and this is the other reason. This is the this would actually be me slowing down, and the previous example with hydrogen is the treadmill speeding up. So let's think about this using rate laws. Okay, so we're removing nitrogen. So in this example, we're removing nitrogen, all right? Okay, so which way does this reaction shift? It shifts towards the reactants, right? It shifts this way because you removed a reactant. You removed a reactant, so it has to replace that reactant. So in this example, the reaction's moving backwards. So at this moment, you might think, oh, the reverse reaction is speeding up, right? Because if the reverse reaction speeded up, won't it shift it backwards? Yeah, but that's not the reason this reaction moves backwards. This is the reason. Okay, the moment, so remember, we got to think about the rate laws. Here's our forward rate law. So this is rate forward, and here is rate reverse. We're removing nitrogen. So what happens to the forward rate law the moment we remove nitrogen? This value changes how? This value right here. It goes down, yes, because we removed nitrogen. This number goes down, so the whole forward rate law slows down. What happens to the reverse rate law the moment we remove nitrogen? Look at the reverse rate law. What happens to that reverse rate law? Nothing. Nothing. I didn't change anything about the reverse rate law. All right? So not decrease. Does not change. The reverse rate law does not change because it does not include nitrogen in it at all. So in this example, where the forward reaction slows down and the reverse reaction stays the same, we will see an overall shift towards back to the reactant side because that forward direction slowed down. So this is the example of two ways to go flying off a treadmill. Either you slow down or the treadmill speeds up. So in this example, you slowed down. And so we still see an overall net effect of going flying off the end of the treadmill, all right? So that is a common mistake that students will make. They'll say, oh, okay, you remove nitrogen, obviously it moves backwards. But it doesn't move backwards because the reverse direction speeded up. It did not speed up. It's because the forward direction slowed down. And that is an important idea that only comes out when you inspect the rate laws. And that's the real Le Chatelier's principle. But what we are doing, just the quick and dirty way, just helps us to predict the direction. But there's different ways we can achieve that. Okay, so that is concentration. Reaction shift forward and backwards. We can use the quick and dirty way to predict which way it goes, but really it's about inspecting those rate laws and how are you changing those concentrations relative to the forward and reverse rate law. So now let's do changes in pressure. This is the third way we're going to do it. So this is really only important when gases are involved. And so again, I'm going to teach you the quick and dirty way, and then we'll do it the real way. Okay, so the quick and dirty way with gases is gases will, thinking about gases, it's really easy to change their concentrations and pressures of a gas sample by either squeezing on the container or expanding the container. So gases are really, I guess, sensitive to volume changes, to like increasing the pressure or lowering the pressure by expanding the container. So this is Le Chatelier's principle when you have an all-gas system where there's an unequal amount of gases on your products and reactant side within your chemical equilibrium. So here's just a random chemical equilibrium. 1A like mole gives you 2 moles of B, which is also a gas. So here is the easy way to predict which way it goes. Okay, so if you squeeze on a container, on a gas container, how does the pressure change at that moment? It goes, if you squeeze on it, the pressure goes up. All right, so when you increase the pressure of your equilibrium, it doesn't like that. So what it's going to do is try to relieve itself of that increased pressure by shifting to the side with less moles of gas. So if I squeezed on this reaction, if I squeezed on it, it's going to shift to the side with less moles of gas. It's going to shift to A because there's less moles of gas on that side. Versus if you expand on your container, you lower the pressure. So the reaction is going to try to make up that loss of pressure by making more moles of gas. So if you expand on the container, it's going to shift to the side with more moles of gas, right? So here's my analogy. Pretend I'm a crazy plant lover. I love plants. I like buying like little potted plants and stuff and putting them in my house, okay? But I'm at a point where I can't like buy any more plants. All right, I'm kind of at max capacity of my plants in my house. So I'm at equilibrium with my number of plants that I have. I have a set number of plants. Okay, so what happens if I move into a bigger house? What am I allowed to do? Get more plants, obviously. You can get more plants. If I move into a bigger house, if I expand my container, I can buy more plants. So you shift to the side of the reaction that has more plants on it. But what if I have to downsize my house and I have to move into a small apartment? What do I got to do? I got to get rid of plants. So which way in the reaction do you shift? The side with less plants on it. So that's the analogy, okay? So if you have more room to grow, you can go shift to the side that has more moles of gas. That is the quick and dirty way to do gases when looking at pressure. I'll add a note here. So when we're expanding and compressing our vessel, our container, we're at that moment either increasing or decreasing the pressures of A and B, the partial pressures of the two gases in the equilibrium. Sometimes you'll see examples that'll say, okay, well, what if you add an inert gas to this vessel? So let's say I add helium gas to this reaction. Adding helium gas to this reaction increases the total pressure of the vessel, but it doesn't disrupt the rate laws at all. And the reason is if you wrote out the rate laws for this chemical equilibrium, is helium in that rate law? It is not. So it's not going to disrupt the equilibrium. So that's the small note here. Adding an inert gas, something like helium gas or anything that's not involved in the equilibrium has no effect on the equilibrium. It does not disrupt it. And the reason is because helium is not in the rate law at all. All right, so that's a small idea. Okay, so let's do it the real way. Okay, let's go back to this reaction. Here is the K expression. So it's pressure of B squared over A squared. So let's think about this using rate laws. Okay, if we compress this container, so we have like a 1 liter container, now we've compressed it to half a liter. So let's reduce the volume by a half, or by a half. So let's use those Pivnert skills, okay? So, or if you think about like concentration or pressure, if you have your volume, how will your pressure of your gas change? If you have the volume, the pressure will increase, but by how much? By 2. Yes, by 2. All right, so here, if your volume of your container halves, the partial pressure of A doubles. All right, so we're halving the container, so volume, we've reduced it by a half. So you can think if you have the volume, you double the concentration. So therefore, you double the pressure. But remember, in this container, B is also in there. So if you double the concentration of A, or pressure of A, you also double the pressure of B. Both of those double. Both of them double. All right? So if both A and B double, let's go back to the rate law. All right? Again, let's write forward rate equals reverse rate. So the reaction is what? What is it? A goes to 2B. That's my equilibrium. So that means that my rate law is obviously rate constant pressure of A equals rate constant pressure of B, but it's squared. So let's go back to chemical kinetics. What happens if we double the pressure of A? How does the forward rate change? It does what? Doubles, right? Yeah, because what? Pressure of A, it's first order. It's first order. So if the pressure of A doubles, doesn't the forward rate constant, so this is the rate of the, overall rate of the forward, doubles. Okay? So what happens if you double the concentration of B? How does the reverse rate change? Is B also first order? It is not. It is second order. So what happens here? The rate of the reverse reaction actually gets multiplied by 4. So that is your reverse rate and your forward rate. So we see that the reverse rate, both the forward and reverse rate increase, but which one increases more? The reverse. So if the reverse increases more, what net effect should we see? It should shift backwards. And is that what the quick and dirty Le Chatelier predicts as well? If we squeeze on the container, it goes backwards. That's exactly what it says. And the reason is because the reverse rate increases more because of this 2. It's because of that 2. It's screwing us up in our rate laws. Okay, both of them increase, but the reverse rate increases more. All right, so that's the real way to inspect that. So let's do the same thing, but if we expand on the container, it's the same exact idea. So if we expand on the container, we're doubling the volume. Concentrations are going to go down. So what we see is that the partial pressure of A halves. All right? The partial pressure of B, it's in the same container, it's in the same volume, also halves. So I hope you see where this is going. It's the same exact thing. If you have a reactant that's first order and you have the concentration, the rate, how will the rate change? It will also halve. So what we see is if the pressure of A halves, when we expand on the container, the rate of the forward direction also halves. But what happens to the rate of the reverse direction? Does it also halve? Nope, it goes back down by 1/4 instead because it's 1/2 squared. So the reason this one was 4 is because it was 2 squared. This one is 1/2 squared, which is equal to 1/4. So we see both of those rate laws, the forward and reverse rates, they both slow down, but the reverse rate law slows down more. And so we see an overall shift to the product side, which is exactly what Le Chatelier's principle predicts. So it all has to do with rate laws. So that there's no going away with those, unfortunately. Okay, so that's the real way. All right, here's something else, okay? Which of these equilibria do you think are unaffected by volume changes? All right, so the whole idea is if I, move into a bigger house or smaller house, right? I can either buy more or less plants. I shift to whatever side of the reaction has less or more moles of gas. But in these examples, all right, if we want to look for the reaction that's unaffected by volume changes, the idea here is if there's no change in number of moles of gas on each side, there's no way for the reaction to relieve itself. So in this case, I like to just think, okay, squeeze on this reaction. If you squeeze on this first one, it's going to shift to the reactant side because there's less moles of gas. In this case, delta N equals -1 because there's 1 mole of gas here. Oh no, it's +1, sorry. It's +1 because there's 1 mole of gas on the product side, 0 moles of gas on the reactant side. The second reaction has 0 moles of gas on the product side, or sorry, reactant side, 4 moles of gas on the product side. So delta N here is +4. Both of these reactions, you squeeze on them, they move backwards. The third reaction, 2 moles of gas on the reactant side, 1 mole of gas on the product side. Oh no, did my pen die? So delta N is what in this example? The C. And C. It would be, oh, there we go. All right, it is delta N, so there's 1 mole of gas on the product side. Remember, delta N is products minus reactants, so this is -1. You squeeze on this container, it moves to the product side. In the last one, we see delta N is 0 in this last example because there are 2 moles of gas on the reactant side and 2 moles of gas on the product side. So if you squeeze on that, is there any way to relieve the pressure? There is not. There is not. So we see that in this case, in D, that's the correct answer. There is no effect in the rate laws or the chemical equilibrium. There's no disruption when we change the volume of D. Or you can think about, if you want to inspect the rate laws, is if you squeeze on these containers, you'll see that the forward and reverse rate increase equally. And that's why there's no disruption. Okay, so that is the second way we're going to do disruptions. And now let's look at the last way, and that is temperature, right? And as always, we will do the quick and dirty way to just predict which direction, and then we will learn the real way to inspect these shifts in chemical equilibria. So the last way we will look at disruptions of chemical equilibria is temperature. And so the quick and dirty way to do temperature changes is just to treat temperature as or treat heat as a product or reactant. So for an endothermic reaction, delta H is positive, right? Heat is a what? Product or reactant. If you're holding an endothermic reaction, what does it feel like to you? Cold. So the reaction is taking heat from you. So that means heat is a what? It's a what? It's not a product. Because if it was a product, wouldn't you, because remember, you're the surroundings. So you're holding the reaction. It gets colder. The reaction is stealing heat from you. So that means heat is a reactant in an endothermic process. So heat, I'm going to just call heat triangle. Okay, heat, we're just going to call it triangle, right, is a reactant in an endothermic process. Versus when I do a big explosion, all right, an exothermic process, heat in that type of reaction is a product, right? Because when we sit here and we see explosions, what we're seeing is the product being formed, which is heat, triangle, after the course of the reaction, all right? That's an exothermic process. Remember, you are the surroundings, so when you see heat coming off, when you feel it getting hot, it's because the reaction is releasing heat as a product, right? And so now it's really easy, because if you treat triangle heat as a product, if you heat up an endothermic process, you add triangle, which way does the reaction shift? Just do it like all the other stuff. It goes forward, yeah, that's exactly right. If you cool an endothermic process down, you're removing triangle. So which way does it shift? Backwards, yeah. So now it's just like it always was for other examples, as long as you place triangle on the correct side. So let's look at an example. I think there was a question about this on a pre-lab, so hopefully you'll get it now. For, I think, the solubility lab, I think. Yeah, okay, so here we go. All right, so consider an exothermic dissolution process. Calcium hydroxide solid, and you dissolve it into aqueous. So if I tell you this is exothermic, where do you put triangle? On the product side. Okay, so it's exothermic, so triangle's right there. So what if we heat this reaction? So that means we add triangle. We increase the concentration of triangle. So which way does this reaction go? It goes backwards. I like the head nods. It's just like a lot of like, oh, it goes that way, it goes that way. That's good. That's called active learning. All right, but what if we cool the reaction? So what is that? We're not adding triangle. If we cool something down, we're actually removing triangle or heat. So if we remove triangle from this reaction, it shifts forward. Okay, so note the states here. The solid is the reactant. The dissolved aqueous form is the product. So what does that mean about this solid? Is calcium hydroxide more or less soluble at higher temperatures? At high temperatures, you add triangle. If you add triangle, doesn't the reaction move to the solid side? So what does that mean about this solid? It's actually less soluble, yeah, at higher temperature. It's less soluble. That's weird. But didn't we talk about that earlier in chapter 13? There are a handful of solids that are less soluble at higher temperatures. This is a reason that predicts it, but it's also due to entropy as well. And we'll look at that in chapter 19. All right? So yeah, we see that this specific solid is actually less soluble at higher temperatures. All right? Do you remember this pre-lab question on a lab? Maybe? Yes, okay. All right, now it's making sense? Okay, yeah, once you just know where to put triangle, then it's not so bad. Okay, so here's an endothermic process. So that means triangle is a reactant. So if we heat the reaction, this reaction moves forward. But if we cool it, it goes backwards because we're adding or removing triangle. So let's interpret that now. What does that mean about KCl? Is it more soluble at high temperatures or low temperatures, do you think? At high temperatures, because adding triangle pushes it to the aqueous side, to the dissolved side. But that's not what I asked here. Is KCl more or less soluble at higher temperature? It's actually more soluble, all right? So yeah, KCl is more soluble at higher temperatures, which is what most solids do. Okay, more soluble at higher temperatures. Okay, so let's put it all together in this example. And I think you'll do this in LCP too. What's cool about chemical equilibria is when we can find equilibria where the reactants and products are different colors, because then you can visually see what's more present, reactant or product, based upon the color changes. So here I have a chemical equilibrium. I know it's an equilibrium because of the double arrow here. All right, so here I see the reactant is yellow, but the product is red. It's blood red. Okay, it looks like blood. Okay, if you think about blood, the components of blood, hemoglobin, heme in the center is an iron ion, and so we see here this also contains iron, so it kind of makes sense. Similar properties here, the blood red color we see. Okay, but what's important here is I have some observations recorded here for you. And based upon this chemical equilibrium and the observations, I want you to tell me, is this reaction endo or exothermic? So you put this reaction in a cold water bath and it turns red. But then you put it in a hot water bath and it turns yellow. So tell me, is this an endo or exothermic process? Your strategy should be put triangle somewhere and see, does it match your observations? If it doesn't, then just put it on the other side and see whether it matches your observations. So what do we think? Where should we put triangle to match these observations? It turns red in a cold water bath and yellow in a hot water bath. Triangle should be on the reactants or the product side. Why don't we just test it? I don't know, right? I look at this and I'm not quite sure, so let's just test it. Let's just put triangle right there. Okay, put it right there. Heat it up. What color does it turn? It should turn red. Is that what we saw? No. So should triangle go on the reactant side? It should not. So let's put it on the other side. Right there. Let's put it there. Now test it and see if it matches your observations. Heat it up. Which way does it turn? Yellow. Cool it down. It turns red. And that's exactly what we see. So with those interpretations, it means this reaction is what? Endo or exothermic? Exothermic. So I can't just look at those colors and be like, yeah, that's exothermic. No, I need to test it out and put triangle in the appropriate place to see whether it matches my observations or not. Okay. So let's put all of this together and see, and just tell me left or right, forward or reverse, does this reaction, with these different changes, which way does the reaction go? So I give you the evil Born-Haber reaction. All right, and I want you to tell me with these disruptions, which way does the reaction shift? Also look at the other piece of information I give you. It's not just the chemical equilibrium, but I also tell you that this is an exothermic process. Okay, so what if we increase the concentration of nitrogen? Which way does the reaction go? Forward or reverse? Forward, yes, okay, forward. Because you add a reactant, pushes it forward. So we're putting all of the concepts together now. What if we decrease the hydrogen concentration? It moves backwards, yes, because we're removing a reactant. I'm really bad at my lefts and rights, so I've switched to forward and reverse. Okay, now think about this one. What if we add HCl, which is it's an acid, and so what that does is it neutralizes or removes NH3. So essentially what this is doing is removing NH3 concentration. What's that going to do? Push the reaction forward, yes. Because it's easy enough for me to say, oh, remove ammonia. But like, how do you remove ammonia? Well, you can neutralize it with an acid, all right? So that's how. Okay, what if we increase the pressure of the reaction vessel by squeezing on the container? So let's squeeze on the container. Which way does it go? Forward, yes, because we want to move to the direction with less moles of gas. There are 4 moles of gas on the reactant side, 2 moles of gas on the product side. So if we squeeze on the container, we increase that pressure. To relieve it, we shift to the side with less moles of gas, right? Okay, what if we expand the volume of the container? It's going to do the opposite. It's going to shift to the side with more moles of gas. We can buy more plants. All right. What if we add an inert gas to the container like helium? Nothing. Yes, it does nothing because helium is not in the rate laws for this ammonia reaction. What if we heat or cool the reaction? So here's the piece of information that we didn't quite use yet. I told you it's exothermic. So that means triangle is a product. So heat it up, the reaction moves backwards. If you cool it down, it goes forward, right? I love Le Chatelier's principle. It all comes together, follows the same kind of trends each time, all right? But there's more details to it, rate laws that kind of highlight the beauty of how it always works, that even when we do the quick and dirty way, if you inspect the rate laws, it's still consistent with what we see. All right, and so I showed you the quick and dirty way for temperature, just treating heat as a triangle, as a product or a reactant. So let me tell you the real way. The real reason your equilibria shifts, and it has to do with the Arrhenius equation, because let me ask you, when you heat up a reaction, how does the rate change? How does the rate change when you heat it up? Hot reactions always go faster. Always. But what was the detail? What was my Jeff Bezos example that I had? All right. If your reaction is already going slow, adding heat makes it go a lot faster than if the reaction is already going fast. All right. So this is the real way. This is the real reason why chemical equilibria shifts when we heat it or cool it down. All right. And it has to do with the energy diagram. So right now, this reaction has what sign of delta H? What sign? You start here, you end higher, so delta H is what sign? Positive. So that means this is an endothermic reaction. Yes, this is endothermic. All right? That's an endothermic reaction. Here are your reactants. There's your products. All right, so that means if I just wrote out like a generic reaction, this is endothermic. You go from reactants to products, triangle is a reactant. All right, when we have a positive delta H. Okay, because here's the thing. Okay, so yes, when we go in the forward direction, delta H is positive, but this is a chemical equilibrium. So that means you have a reaction rate going forward and you have one going backwards. So it's going back and forth, back and forth. So when we heat up this reaction, the forward direction gets faster. But when we heat up this direction, or this reaction, doesn't the reverse also go faster? but then which one gets faster more? That's the question that we need to ask ourselves, and this relates back to chapter 14 and the Arrhenius equation. K, your rate constant increases when temperature increases. So higher temperatures, larger rate constant. But what we see also is that reactions go fast when your activation energy is smaller, right? Because here, when you do this reaction, do the forward and reverse reactions have the same activation energy? They do not. And so when we heat this reaction, the difference in activation energy has a different magnitude of effect of how rate constant changes. So remember, this is what you need to get out of, is large activation energies are more sensitive to temperature changes, okay? If you give me $1,000 versus if you give Jeff Bezos $1,000, it has a bigger effect on me because I have a large activation energy, I'm already going slow. Versus Jeff Bezos, yes, he gets $1,000 richer, but it doesn't have as much of an effect on him. So let's think about this. Okay, this is an endothermic reaction. When we increase the temperature, how does the forward direction rate constant change? Does it get faster or slower? It goes faster, so we see the forward rate increase. All right, we see the forward rate increase. But what happens to the reverse direction? Does it go down? No, it also goes up. But does it go up as much? It does not. So it goes up, but only a little bit. And the reason is because this reaction, the reverse reaction, is already going fast. All right, so I like to think, okay, both the forward and reverse reactions speed up, but the forward direction speeds up more because it's already going slow. That's what you need to think of here. So what we see here, okay, remember, K is also related to your rate constants. It's the forward rate constant over the reverse rate constant. So you have a big number over a little number, and that is K, Kc. So we see that the value of K actually gets larger. The value of K gets larger. So what we see here, you know, when we think about endo and exothermic reactions, triangle heat is not a product or reactant. The reason there's a shift in equilibria is the value of K, your equilibrium constant changes. So Kc actually gets larger. The value changes. So if you like look at a textbook at like 25 degrees, a reaction has a K of 50, it'll have a different K value at 100 degrees Celsius, all right? And so for this reaction, the value of K gets bigger. So if K gets bigger, what are you gonna have more at equilibrium if K gets bigger? More products. So is that consistent with what Le Chatelier's principle predicts? You heat the reaction up, it shifts to products. Yes, and so that's consistent, yep. Right, so that's for an endothermic reaction. When you change temperature, the value of K, your equilibrium constant, actually changes because your rate constants change unequally. Okay, so we did endothermic, so let's do exothermic. Same idea, but see, your graph is just different now. But remember, it's still the same. Reactants, products, there's your equilibrium, reactants, products, but this time triangle's your product. A large activation energy is more sensitive to temperature changes. So when you heat up this reaction, the forward direction gets faster. But what happens to the reverse direction? It also gets faster, but it gets faster more because you have a large activation energy in the reverse direction. Large activation energy means already slow reaction. So that means if we calculate the value of Kc, which is the ratio of Kf over Kr, we see that the forward rate increases, but the reverse rate increases more. So you have a small number over a bigger number in the denominator. So we see that the value of Kc actually goes down. So when you heat up this reaction, the value of K gets smaller and smaller and smaller. So we see heated up, you actually form more reactants over time. And is that consistent with our quick and dirty way of Le Chatelier? It is, yes it is. You heat it up, you make more reactants, which is consistent with getting a smaller and smaller K value. So the only way we can actually change the value of K for a chemical equilibrium is by changing the temperature. When we made disruptions by just like concentration changes or pressure changes, we never change the value of K. We're only ever comparing like a Q and K condition to one another and seeing how it gets back. But with temperature, you're actually changing the value of K. And that's why there's a shift. All right, so that is chapter 15. Let me do my demo. And we'll do the same thing. And you think about temperature, how it affects chemical equilibrium, but then relate it to the real way. So Le Chatelier's principle is really cool because this is usually where we show colored reactions because it's easier to see what dominates at what conditions. So here I have a demo between N2O4 and nitrogen gas, or sorry, NO2 gas. And so what's cool about this, this chemical equilibrium is that the reactants is colorless and the product is brown, all right? So we can clearly see what dominates at different conditions. So here is a mixture of those two gases, N2O4 and NO2. So what I'm gonna do is put one in an ice bath and one in a hot water bath, and we'll see how temperature affects this chemical equilibrium. Ooh, you can already see it going off right now. Okay, so in the hot water bath, how is it different than the cold water bath? Do you see the difference? Yes, the hot water one, a lot more brown than the cold water one. And what's cool about this is I can change it, all right? Because these are reversible reactions. You can just disrupt it as much as you want, and you can switch them back and forth, and we'll see slowly they'll shift themselves to get back to equilibrium. And so what you see, the cold water, it's going to take a little bit of time, is that this one, the one in the hot water bath is getting darker, the one in the cold water bath is getting lighter. So based upon these observations, is this an endo or exothermic reaction as written? Just looking at it, these reactions, you won't be able to tell. What you probably need to do is just put triangle somewhere in this reaction and figure out, does it match your observation? So let's put triangle somewhere. Let's put triangle right here. Okay, if I put triangle on the product side, you heat it up, what observation should you see? It should get colorless, it should become lighter. Is that what we observe here? It is not, so that means triangle is not in the right place. It is right, it should go right there. That adding heat makes it turn a lot more brown than in the cold water bath where it's a lot more colorless. It's still a little brown because there's still a little bit of that product in there, but a lot less of it than in this container. So that means that this reaction as written in this form is what? Endothermic. Okay? All right, so if it's endothermic, why is the equilibrium shifting? What's the purpose or the significance of this disruption? As the temperature increases, the value of Kc or Kp or whatever, how is that changing? Remember, changing temperature is the only way we can actually change the value of K. All of our other things, it was always Q versus K. So we see here, as temperature increases, the value of K actually increases. Yes, it increases because it has to be consistent with making more of the brown product, right? And again, putting it all together, why does Kp increase? It's because the forward reaction increases more than the reverse reaction. And to prove it, just draw a generic endothermic reaction. All right, an endothermic reaction has a large activation energy in the forward direction. So when you heat this reaction up, both the forward and the reverse direction get faster, but the forward increases more because it's already going slow. All right, so that's the demo. Told you a demo a day. I'll do a cool demo on Wednesday when we do get further into chapter 16. Okay, so we got 25 minutes left. I'm gonna start chapter 16 now, all right? So that's chapter 15. That means chapter 15 homework is due on Monday. It's on Monday. But because Monday's a holiday, I'm gonna move it to Tuesday, all right? So instead of Monday at 10:15, it'll be Tuesday at 10:15. But remember, chapter 15 is on midterm too, All right, so it's in your best interest to do as much of it as you can. But what this also means is that this part 1 of chapter 16, this homework set, is not due until after midterm 2. So you're going to basically be assessed on it before the homework set is due, which I'm fine with because I like to stay consistent with my policies. But do keep that in mind. It's in your best interest to do some of the homework to help prepare you for exams. Okay, so I told you we're in the middle of this big K tunnel. We're talking about equilibrium constant. I told you we're going to talk about equilibrium constant for a long time, including this chapter. So in chapter 15, we just looked at basic generic chemical equilibria. Now we're going to look at chemical equilibria specific for acids and bases. So it's still the same big K we've always been talking about. It's still forward rate equals reverse rate when we're at equilibria, but it's just specifically for acids and bases. And honestly, the ICE tables, they're easier in this chapter because all the stoichiometry is a 1-to-1 ratio. So we're going to look at acids and bases. So if you are going to review some Chem 1210 content, recall there are 7 strong acids. Everything else is weak, all right? We're still learning about big K. We're just going to learn about more Ks. We talked about Kc. We talked about Kp. In this chapter, we're going to learn about Ka, Kb, and Kw. So we're going to introduce more Ks. But it's still the same K. It's still products over reactants. So before we move on, let's just recall what those 7 strong acids are, because this is helpful because how we calculate pH is different for strong acids and weak acids. So the best thing to do to memorize or differentiate that with acids at least is memorize the 7 strong acids. That means every other acid is weak. So the 7 strong acids, if you look at the periodic table, can help you. Within the halogens, your binary strong acids are HCl, HBr, and HI. So it's basically all those halogens except HF. And we'll learn about why HF isn't a strong acid in a little bit. All right, so those are 3 of them. Those are our binary acids, meaning it's just H plus and like a monoatomic anion. So then there's 4 other strong acids. They include HNO3, that's nitric acid. You've probably used that in lab. What else is there? Sulfuric acid, H2SO4. You've probably used that in lab. And then the last 2 are the chlorate acids, so HClO3, that's chloric acid. And the last one is perchloric acid, so HClO4. Those are your 7 strong acids. So if you ever encounter another acid and it's not one of those 7, it's a weak acid. So if I said carbonic acid, is that a strong acid? It's not, so it's a weak acid. Phosphoric acid, also a weak acid. Any acid that's not one of those 7 is weak, and that's very important because all weak acids have a K value that we will talk about here soon. Okay, so this chapter is a long one. Basically, chapter 16 and 17, it's like one big long chapter, but we split it up into 2 because it's just a ton of material on acid-base chemistry that we'll be talking about for like the next 3 weeks. So this chapter I have split up into 2 sections, midterm 2 material, midterm 3 material. So midterm 2 will stop right around slide 24, where we are just going to learn about different types of acids and acid categorization, and we will calculate pHs of just strong acids, just the strong acids. Weak acid calculations, we will wait until midterm 3 to learn about that, but it's not bad. It's just an ICE table, but you always make an approximation, so it's not bad. Okay, so acids. We are actually going to start with pH calculations first and then move on to the categorizations of the history of acid-base chemistry. And there's 2 homework sets here too, but I'll remind you that this homework set, this first one for chapter 16, won't be due until after midterm 2. Okay, so acids, bases. So historically, and there's a bit of history here too, and we will look at the categorizations of acids. Acids and bases have been categorized by their behaviors. And so way back when things were more archaic and I guess chaotic, and scientists would taste the chemicals that they were using, they often found that acids were sour in taste. Most of the foods that we eat are sour, and we like it that way. All right, most everything we eat is slightly acidic, versus bases were identified by their bitter taste. And that's kind of how they categorize things. But it also has to do with their properties that we'll look into momentarily. It actually has to do with their structure and their different categorizations. We'll learn about these categories a little bit later, but let's learn about pH first. So water, so in general, acids, you know you have an acid when you see H+. Typically with strong bases like NaOH, KOH, those are both strong bases. Bases typically have a hydroxide. Now, add H+ and OH- together. What do you get? Water, yes. A lot of students are like HOH. And I'm like, what is that? And it's water, yes. And so what we see is acid plus base gives you water. So water is important here. It's an important factor when looking at concentrations of how acidic something is, H+, or how basic something is, OH-. Water is kind of an ingredient and a factor there. So what we'll see here very shortly is that the concentrations of H+ and OH- are typically very, very, very small in the solutions you work with in lab. They're very small. Do you like writing scientific notation? Do you like doing that? No, I don't. Okay, times 10 to the -8, like writing that a billion times, I don't like that. All right, so these are very, very small numbers. So what we use to better communicate how big or small these numbers are when it comes to H+ and OH- concentration is use a negative log scale. And this is where the values pH and pOH come from. So I'm sure you've already heard of the idea of pH. Well, what is pH? pH is actually just the magnitude of H+ present in your solution, in your sample. So P is just a function, all right? So pH is the negative log of your H+ concentration in your solution. Same idea, pOH, which oftentimes these two things are related to each other. You'll usually see pH, not so much pOH. But pOH is simply the negative log of the OH- concentration in your solution. And the beauty here is when your solution is made in water, right? Because water has that H+ and OH- component in it, pH plus pOH is equal to 14. But this is only true at 25 degrees Celsius. I'll point that out. And I'll tell you why in a little bit. All right? So P just stands for negative log. All right, so pH is negative log of your H+ concentration. pOH is negative log of your OH- concentration. P bananas is what? The negative log of your banana concentration. That's all what P means. It means negative log. That's it. Because you'll see P attached to a lot of things. Like there's pKa, pKb, pKw. All it means is negative log of that number. That's it. Okay? So let's practice using this. So if I tell you that you have a solution and its H+ concentration is 1 times 10 to the -5, that's an annoying number to write. So instead, I'm going to use a pH scale instead. So if I take negative log to the 1.0 times 10 to the -5, you tell me what your calculator says. It says 5. So what would you rather write, this number or this number? 5, all right? So what this is, okay, is the negative log scale basically tells you the magnitude of how big or small your number is. It's related to the exponent that's on that 10. And because it's negative log, and this is a -5, that means 5 comes out here, all right? But let's look at sig figs, because you might see, oh, the H+ concentration, the molarity has 2 sig figs. But right now, this pH, it looks like there's only one sig fig, but there's a special rule for logarithms, all right? Because typically, up until this time, usually like 95% of the time, if you see like all your numbers have 3 sig figs, your answer has 3 sig figs, right? But here it's a little bit different because that logarithm, that answer we got, 5, just tells us how many times we move the decimal place. That's actually a counting number. So that 5 actually doesn't count towards the sig fig. So the real rule here for logarithms is the number of sig figs in your molarity is the number of decimal places in your pH calculation. 5 tells you how big the number is, how many decimal places there are. But this, to be completely correct, is actually going to be 5.00. Those 2 zeros have 2 sig figs. All right, so that is the real rule for pH values. The number of sig figs in your molarity is the number of decimal places in your pH. All right, so that means if we wanted pOH, the relationship that I have up here, and of course we're going to assume 95% of the time we're working at 25 degrees Celsius, pH plus pOH has to equal 14, so that means my pOH is, it's 9.00, right? And if we wanted to undo that, if I wanted to know what is the hydroxide concentration in this same solution, to undo a pH value, all right, so here I have pH equals negative log H plus. To undo that, let's say I give you a pH and I want you to tell me the H plus. The H plus concentration is equal to the 10 to the negative pH. So that's how you undo a logarithm. So same thing for pOH. If I wanted the hydroxide concentration, you do the 10 to the negative OH minus, or sorry, pOH. All right, so that means if I have my pOH value, it's 9. That means my hydroxide concentration in this exact same solution is 1.0 times 10 to the negative 9. And again, 2 sig figs because there's 2 decimal places. So it's all consistent. So that's how I undid it. All right, let's just do one more. So let's say I tell you that the pH is 11 for a solution. So that means my H plus concentration is what? 1 times 10. So put this in your calculator. Just do 10 to the negative 11, and you should see 1 times 10 to the negative 11. That's your pOH. Are my sig figs correct here? They are, yes. 1 decimal place, 1 sig fig. Perfect. Good. All right, so that's the concentration of H plus. Look how annoying it is to write that number. All right, that's why we report these values in pHs, because 11.0, a lot easier to report than 1 times 10 to the negative 11. It's a lot of numbers. All right, and so that means my I got my H plus calculation, so I can get my pOH the same way. I always like to just calculate my pOH from my pH. So here pOH is 3.0, so that means my hydroxide concentration is 1 times 10 to the negative 3. Right, same thing, 1 sig fig. Right, so we see here for these examples, whether to tell a solution is acidic, basic, or neutral or not isn't necessarily what is its pH. It actually has to do with what are the magnitudes of H plus and OH minus present in that solution. So the true definition is when you have an acidic solution, your concentration of H plus is larger than your concentration of hydroxide. And that's true in this first solution. This first solution is acidic because there's a lot more H plus than there is hydroxide. 10 to the negative 5 is a bigger number than 10 to the negative 9. The second solution, if you compare those H plus and OH minus concentrations, is actually basic, because there's a lot more hydroxide present. All right, 10 to the negative 3 versus 10 to the negative 11. The true definition of a neutral solution, it is not pH 7. It's not pH 7. It's actually when your H plus concentration equals your hydroxide concentration. It just so happens at 25 degrees Celsius, that is true at pH 7. I will point that out. but at other temperatures it is not true. And we'll look at an example here in a moment. All right, so pH 7, not necessarily neutral. This is the definition of neutral. Okay, so 10 minutes. All right, and I will show you why right now. Okay, so I mentioned water is a very important aspect to talk about H plus and OH minus concentration and pH, because water actually contains H plus and OH minus. And actually, we've been lying to you all this time. So remember back in Chem 1210, and we talked about like pure substances, and we said, oh, if it's, you know, if you can write a formula for it, it's a pure substance. We always said, oh, water is a pure substance. Okay, water actually has its own chemical equilibria. A pure sample of water actually is not H2O copy and pasted a billion times. It's actually a chemical equilibria. We've been lying to you all this time because you weren't ready, but now you're ready. All right, this is actually what water is. In a pure sample of water, here are 2 water molecules. In a water sample, it's not just these multiplied a billion times. What actually is happening is that 2 water molecules will share an H plus with one another. All right, so what's going to happen between these 2 water molecules, one of the molecules is going to donate an H plus to another water molecule. And what the product is look, we have an OH minus, where that one water molecule gave up an H plus, and the other one gained it. And now this is H3O plus, or hydronium. So what happens is, you know, we start with 2 water molecules, but we end up, and this is a chemical equilibrium, with a hydroxide and an H3O plus. But this is essentially the same as H plus, all right? This is actually what's happening in water. It's very, very, very small, all right? This is a chemical equilibrium. How do you know? There's a double arrow. As with all chemical equilibria, they all have K values, Kc values, right? So if you look up the Kc for this reaction, you can look it up. It is equal to 1 times 10 to the negative 14, all right? So that's a really small K value. So this reaction, this equilibrium isn't happening that much in water, but it is still enough, all right, happening in water. So we can write the K expression for this chemical equilibria like always. And so here's the whole written out chemical equilibrium. So it's simply products over reactants. Look at your products. We have H3O plus times OH minus. Do we put water in the denominator for our K expression? No, we don't. Why don't we put water in here? Because it's a liquid. Yeah, so what we see here is that the K expression is simply those 2 products, H plus, H3O plus, and OH minus. And so this is the chemical equilibrium for water. So water actually isn't a pure, like 100% pure like we always thought. This is happening to a little extent. But here's the thing, chemists, we are lazy, and H3O plus is the same as just acid H plus. So we will oftentimes write this as H plus times OH minus. And the idea here is that H3O plus is the same as H plus. It's H plus plus a water. We just get lazy and we don't feel like writing the other water, like the water molecule. So they're the same thing, right? So what you'll learn here is that Kw, this is what you want to know. Kw is equal to the H plus concentration times the OH minus concentration. Kw is a constant, it's a value. It's 1 times 10 to the negative 14, all right? Okay, so we got a K value, we got a K expression. Let's do an ice table. Let's calculate equilibrium concentrations and pH of a pure sample of water, and I give you the K value. This is the exact same ice tables we've always been doing, all right? But this one's a little bit tricky because I don't give you initial concentrations. So here's the trick. Start with a random amount of water. It doesn't matter how much because it doesn't show up in the K expression, all right? So I'm going to start with a random amount of pure water and none of the products. Just like chapter 15, which way does this reaction have to go? Forward. So what do I write in my change line? Minus 2x plus x plus x. Great. So I add up my columns. So the equilibrium concentration of Water is N minus 2x, X of H plus, X of hydroxide. All right. Like always, we always put the equilibrium line into the Kc expression, but in this case it's Kw because this is the equilibrium of water. Do I actually care about this N minus 2x term? I don't, all right? That's why it didn't matter what number I put in here, because this value does not end up in the K expression at all. So I just ignore it. So what do we see? Kw equals H3O plus concentration, or H plus, whatever, if you want to get lazy, times hydroxide concentration. So we see Kw equals X squared. Do we know the value of Kw? We do. It is 1 times 10 to the negative 14. Like all ice tables, we solve for X. So this does not require the quadratic, it just takes square root of both sides, so it's quite straightforward. And so what we see is that X is equal to 1 times 10 to the negative 7 molarity. All right? And now you ask yourself, is X, is that my answer? What does X represent? Look at the ice table. What did you assign that X variable as? That X is equal to the concentration of what? H plus and the concentration of hydroxide. How do I know that? Look at your ice table. At equilibrium, you have an X amount of H plus and an X amount of OH minus. So that means they're my equilibrium concentrations. Pure water has a H plus and OH minus concentration of 1 times 10 to the negative 7. So what is the pH? 7. It is 7. Yes, it's 7. With 1 sig fi, no, 2, because Kw is, there, 7.00. So there we go. pH is 7. So here we just proved water, pH neutral water is pH 7 at 25 degrees Celsius, because at 25 degrees Celsius, Kw is 1 times 10 to the negative 7. Kw is 1 times 10 to the negative 14. So if pH is 7, that means my POH is also 7. Okay. And so where that whole pH plus POH equals 14 thing comes from, this is where it comes from. It's if you do Kw equals H plus concentration times OH minus concentration, if you take the negative log of both sides, all right, negative log of Kw, and here is Kw, equals 14. So that is why pH plus POH equals 14, because you're taking the negative log of both sides there. All right. Okay, let's just do one more. We just proved that at 25 degrees, neutral water is pH 7. We know it's neutral because H plus is also equal to OH minus concentration. Let's do it again, but this time let's do it at 50 degrees Celsius. Note, at 50 degrees Celsius, we have a different K value. We learned that heating up reactions changes the value of K because your forward and reverse rate constants change unequally. So let's do the same thing, but with a different Kw value now. But the process is the exact same. We have pure water, it's just at 50 degrees. We have a different Kw, so the process is the exact same. Throw in a random amount of water. We lose a little bit of a 2x amount of that water, but we gain an X amount of acid and base. At equilibrium, we're going to have an X amount of H plus and an X amount of hydroxide. Does the amount of water matter? No, so I'm just going to ignore it. This goes into the Kw expression, which is, again, just your products multiplied by one another, so H3O plus times OH minus. So that means Kw is equal to, X squared again. But look, it's different this time. Kw isn't 1 times 10 to the negative 14. I gave it to you. I'm telling you, at this temperature, Kw is 5.5 times 10 to the negative 14. I gave it to you. It's right here. It's right there. So all you do is you take the square root, and you get X is equal to something. Dumb fingers. Okay, dumb fingers. Kw is equal to, I didn't write it down. Cool, okay. 5.5 e negative 14. 2.3 45 times 10 to the negative 7 molarity. All right? X is equal to the concentration of what? H plus concentration? Yep, because that's what it is in the ice table. So if I take the negative log of that number, so negative log of that number is 6.63. Is this water acidic at 50 degrees Celsius? That is correct. It is not acidic. It is what? pH neutral. It is neutral, but it's 6.6. I thought pH neutral was 7. That's only at 25 degrees Celsius, because continue on. X is equal to the H plus concentration, but isn't it also equal to the hydroxide concentration? Look, both of them are X in the ice table. So what we see here, does POH plus pH equal 14 in this example? It does not. It actually equals whatever negative log 5.5 times 10 to the negative 14 is. So what we see here is that this water is still neutral, because the fact holds true that H plus equals OH minus concentration. It just so happens this happens at a different pH than pH 7. All right? So yeah, we will stop there. We will stop there and continue on Wednesday next week. So a week from today, no class on Friday. We'll finish up this part of chapter 16. We'll do some review for midterm 2 as well. Yeah, so have a great weekend. I still have office hours today, so.